Hey everyone, and welcome to Measuring the Heavens. And so, we're going to take a look at it. There's some questions, interestingly, in the book of Job, where it says, "Can you fasten the chains of the Pleiades or loosen the belts of Orion?" And these are our best guesses as to what constellations this could be referring to. Those are the two particular phrases in Hebrew. And so, what were they? Well, they must have been common knowledge to Job in his day. And they're of course, interesting constellations, and probably how most of us would respond is something along the lines of, well, God, I don't really know what those constellations really are. Let me see where they are on this new app, and I'll get back to you. What do those constellations actually look like? Kind of like this. Here's the Pleiades star cluster. And there are kind of 7 main stars, but there's a large grouping of stars that we'll take a look at in future weeks with regarding some of the properties of the Pleiades star cluster and how you can estimate the age of the Pleiades star cluster based upon some interesting properties of its stars. Belt looks something kind of like this. You have 3 stars. Now, there's of course something very interesting about Orion's belt in particular, in that those 3 stars are not even remotely close to each other. They just appear to be from our perspective. It's called an asterism. But by and large, I mean, you're essentially looking into the past. Every time you look into the night sky, you're not seeing things as they presently are, but of course as they once were. So the Pleiades star cluster, on average, you'd be seeing them as they were a good 500 years ago. In Orion's belt, as I mentioned, those 3 stars in particular, you're seeing one of them about 800 years ago as it was, and then another 1300 years ago, and so on and so forth. And of course, the closest star to us is a good 4.3 light years away. Now, of course, there's something in the night sky that you can see with your naked eye that is so much farther than any of these. It's this nebula or cloudy blur in the sky. But we've got a long way to go until we get to that particular object. So we'll come back to that. And now there's of course something interesting that it says in Jeremiah 31. Now this would be probably a bad way to read various things in the Old Testament, in particular these verses. It says that the one who gives the sun for light by day, the fixed order of moon and stars for light by night, if this fixed order departs from before me, ... so on and so forth, or only if the heavens above could be measured and the foundations of the earth below explored, well, I reject all of Israel's descendants because of all they've done. So this is something that says in the book of Jeremiah, right around the New Covenant, which is, of course, a very exciting section for New Testament believers in the book of Jeremiah. The idea was that a plain reading of Scripture, though of course filtered through the lens of some Greek philosophy and the best science of the day, which was the Aristotelian model of the universe, well, guess what? If you're reading that particular verse, the stars are indeed fixed. None are created, none are destroyed, they're eternal. And there was this idea that existed in various writings that the heavens were perfect, complete, unalterable. Some thinkers who embrace this in particular, explicitly mentioning this, might be Aquinas or Dante, where the curse of sin did not extend into the heavens, but everything changed in one single moment, where there was this new star that appeared in the sky, but the heavens were supposed to be fixed. And that was a really disturbing thing for many people. It's almost a theological puzzle. Tycho Brahe, upon examining this new star that appeared in 1572, amazed and as if astonished and stupefied, I stood still gazing. When I had satisfied myself that no star of that kind had ever shone forth before, I was led into such perplexity by the believability of the thing that I began to doubt the faith of my very own eyes. And so this was a puzzle. If God created the heavens in the beginning, what was this new star, and how should we think of it? I mean, there was endless speculation in terms of what it was. Did it have something to do with political upheaval in some kind of dramatic event that was going to happen in an astrological sense? And there was a lot of speculation. Actually, an old star. It was a star that had died quite a long time ago, and the reason that they were able to see it is because of one of the properties of star death. In particular, he was seeing a supernova, which supernova are really, really bright events, and of course, you wouldn't see the star before it goes supernova in the night sky if it's far enough away. But once it becomes supernova, it essentially becomes bright enough to see, and you could learn some things about where this supernova is, depending on how it moves across the night sky as well. So one of the ways that we learn things about heavens is this. Essentially, it's this technique called the parallax. Now, of course, we could also say, as it says in the book of Jeremiah, if you start measuring the heavens, God is going to cast Israel off forever. Of course, that would be a bad way to read that, which I would certainly hope that no one holds to such, because we could measure exquisite properties with exquisite precision about things in the heavens. So Brahe actually used a technique to measure how far away it was, and he figured out that it was much, much farther than the moon. And it was this technique called parallax. So if you look at this little cartoon diagram, let's say here we are, the Earth in June versus December, and we're on opposite sides of the sun. And a very, very interesting thing is that if the star's far enough away, you really won't see much of anything occurring. You can do this little experiment with your thumb. If you hold your thumb about a few inches from your nose, and then you blink, you see that relative to a distant background, your thumb appears to move a lot. But then if you go ahead and hold your thumb at full arm's length, and you do the same thing, blinking one eye and another eye, you see that the star, or your thumb, appears to move quite a bit less. You can imagine if you go even farther away, those distant objects appear to move less and less and less until you essentially find that there is a background of stars that just doesn't move in June and December. But there are a lot of stars that appear to move, and those would be ones that would be closer to Earth. And so here's just an example of a parallax star on one other side. Then, of course, a nice aside into doing math. This is another way to read the Old Testament, of course. Whenever the Lord says, let us do math, hopefully you don't feel like Ezra did. I'm pretty sure this is why Ezra did that, because he was asked to do math. And here's a cartoon diagram of Ezra setting a pole, pulling hair from his hair, head and beard. It's pretty a little relationship here, and you could go ahead and calculate the parallax angle depending on how much in the distance, depending on how much it appears to shift. So this, of course, just like with your thumb, eventually the movement of the star is going to become too small to measure, the farther and farther away the star gets in particular. So there's a limit of about 500 light years or so, which most of the entire universe is beyond 500 light years. So there was an interesting debate that existed in the 1920s. It was the Great Debate, Shapley versus Curtis. It was an interesting debate that there was, the question was that object that I reasons. It's interesting just kind of reflecting upon this a little bit. I mean, you had two really established ideas. Either one of them could be correct or neither. Two well-established scientists, and maybe it can happen out of fear of control. There could be lots of things. I mean, in terms of science, for something to receive the claim of being scientific, that carries a weight of authority about it. And maybe sometimes these types of discussions can give people the wrong idea that if there's some kind of discussion about something we don't know in science, then we don't know anything. And I feel like a lot of people might feel that kind of tension to admit uncertainty in some kind of area will immediately be seized against it and say, see, everything that you can't explain is wrong. And I've seen that happen a lot. But then maybe in a Christian aspect, we want to have all the answers to all of the questions. And maybe, it can feel fearful to open up the door to consider different possibilities or ideas. Just saying, you're just opening up, this is a slippery slope to hell, so on and so forth. And there are certainly some things that we're never going to have an answer to. Thankfully, this is an example of that. So this is a cool idea. It's basically like having a candle of known brightness. And so there would be a pretty simple relationship here in terms of the measured luminosity compared to the standard or intrinsic brightness of a star, divided by that intrinsic brightness is going to be spread out over a sphere in equally directions, basically. This is an inverse square law. And so it's pretty simple. You can just simply measure the flux that you receive on Earth, and if you know how bright it is intrinsically, you can calculate the distance from that. It's really easy to do. And thankfully, there are different types of standard candles that exist. This was one of the first ones discovered, where we found that there was this interesting relationship between the periodicity in terms of a variable amount of brightness of these types of stars and their intrinsic luminosity compared to the luminosity of the sun. And so this was pretty cool. Basically, if you look at the graph here, you find this is one particular type of Cepheid stars, and stars that had a period of 10 days all tended to have the same type of luminosity. So basically, if you found one of these stars, you could study how long it took the brightness that you measure to decrease and then come back to the brightness you began measuring it with. Basically, it was some kind of sinusoidal or cosine type of function like that. You can go ahead and figure out fundamentally how bright the star is. Cool little story there with Henrietta Leavitt. First discovering this relationship of Cepheid stars, and here's the computing power that figured it out. It was a group of female calculators, essentially, where they as the legend goes, I'm not sure how true it is, but at least this is what I heard. So Dr. Pickering, he took lots and lots of data all the time, and of course one of the things with data is it's great and wonderful, but you need to do some calculations on it. So one of the things that he did is that he would hire a team of graduate students to go ahead and do calculations for him and so on and so forth. Okay, that was great. But then it turns out that the two he had hired, they were two male students, and he found that they were terrible at doing these calculations. And so he said, you guys are so bad that my maid could do a better job. And as the legend goes, his maid could do a better job. And he said, well, women are actually amazing at doing these calculations. And so we began to hire a bunch of them, and one of them just and reflecting upon her life, one biographer noted, she was a devoted member of her family circle, unselfishly considerate of her friendship, steadfastly loyal to her principles, and deeply conscientious and sincere in her Christian life. Carrick. So anyways, it was eventually settled because we found a Cepheid star in the Andromeda galaxy, which settled how far away this object was. It was not part of the Milky Way galaxy. It's hard to fathom and imagine what happened in this short time frame, how our understanding of the universe, that we'll reflect on a little bit when considering the multiverse as a whole, just got much, 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 much bigger than anyone could have possibly. Well, I mean, it's 2.5 million light years away. It pales in comparison. It blows everything out of the water compared to the rest of that. But it turns out our universe is actually quite a bit bigger, just 2.5 million light years. And that leads into something called the redshift. This is an interesting phenomena where we can simply measure how much the atomic spectra of hydrogen is shifted either to the left or to the right in terms of its wavelength being stretched or compressed. And how does that work? Well, I'll come back to this picture, but it works via the Doppler effect. We notice this, of course, with sound. The closer something moves to the speed of sound, the more its frequency changes. We can hear this with an ambulance approaching us and then moving away from us, so on and so forth. Mathematically speaking, it's pretty simple. If the source is moving, so you have the speed of sound, and this would be, and for the sake of stars, it would be the speed of light you put into that equation, and it's pretty basic. Basically, you can go ahead and measure the observed frequency. You know what the frequency is at the source because hydrogen just so happens to do the same thing everywhere in the universe, and there are ways that we can, of course, test that. We'll talk about. But then what spectra? Well, you can have something like this. So let's say here's the hydrogen spectrum, and you can have the entire spectrum shifted to the left in this particular diagram, or it could be to the right. But basically, instead of seeing 656 nanometers in terms of one of the wavelengths that hydrogen atom emits, you find that it's a little bit longer. And the same with all of the other spectral lines. And then you could also see, though, that maybe that 656 nanometer line is a little bit shorter. So that would be a blue shifted spectrum. And it's not just hydrogen. Hydrogen is the most prevalent molecule in the entire universe, so by and large, this is mostly, in effect, looking at hydrogen. But there are many other elements that you could look at. And so there's some really, really interesting things that were happening and had been. And this really was a slow process of ideas building upon themselves. It took many hundreds of years, new observations, new technology, so on and so forth. And this really, the story, I mean, going from the universe not revolving around us, the heavens are not unchanging and immutable, there's not some entity pushing and keeping planets in their orbits, so on and so forth, really started to pick up with the equations of general relativity. And of course, there were some immediate tests that were proposed describing the anomalous orbit of Mercury. We'll come back to that when discussing dark matter. But then also that we should see starlight shifting. And something else interesting that is predicted by this is that we should see some kind of redshift. What does that look like? It looks something like this. So here's an example of the electron transitions for hydrogen. This basically is a description of why you see very, very specific wavelengths emitted by the hydrogen atom. And their energy levels here are quantized. Hydrogen will always emit photons with exactly the same wavelengths and frequencies and so forth. But the interesting thing that we began to find is that the farther away a galaxy is, the more that these lines, spectral lines, were stretched. That was an interesting. If you plot that, so the distance determined by Cepheid stars compared to the velocity, you get some kind of diagram like this. This is really interesting. I mean, this is a phenomena that was predicted to exist, and then we actually measured it. But a good question is there another reason or any other explanation as to why we might see this effect, that the farther away an object is, the farther away a galaxy is, or a particular star, so on and so forth, the more that its light seems to be redshifted. Essentially, it could be losing energy in some kind of way, shape, or form. So that led to a number of alternative hypotheses. So here's the higher light hypothesis. This is an interesting one. So of course, yeah, it's great that you have this set of equations that predicts X, Y, and Z, and then you actually measure that. But at the same time, it'd be good to test alternative hypotheses. And this is an idea where essentially light gave off some kind of energy over time. And so as a result, what you're seeing is not due to the relative motion of such distant objects, but instead it's just the light is losing energy the more it travels. So the light is giving off energy over time. And thus it really only appears to be redshifted. It's an interesting idea, and of course we could ask, hey, what's this? This is one that has been proposed, and it has to do with something related to redshift periodicity and also intrinsic redshifts. So this is the idea that, well, this is not the expansion, but there's some kind of intrinsic redshift mechanism. Basically, the redshift is something that's produced entirely inside of objects and due to their interactions. Something is happening to their photons that's getting changed. So what kind of mechanisms were proposed? Well, one of the big advocates of this was Halton Arp, and he had a number of alternative cosmology ideas, and he proposed, along with a few others, this idea of variable mass. So basically you would have smaller particles at the source compared to the receiver. So whenever we're measuring things like electrons and protons and so on and so forth in the distant universe, we find that their mass is just different in the past. In particular, maybe you could get some kind of redshift type of thing if particles were just smaller the farther away that you go. What evidence did he suggest for this? He said, well, you know what, there's some quasars that are close to the line of sight for some active galactic nuclei, AGN for short. And so, but those galaxies are at a lower redshift. And he said maybe there's something happening here, where these quasars, something is happening to them where they appear to have a much greater redshift than others. And so Alt, ARP, and others interpreted this to mean that there was some unknown mechanism that could produce a redshift like this. But unfortunately for him, as we gained more and more evidence, his hypotheses became less and less plausible as we learn more about our universe. Why is that the case? Well, we now know of hundreds of thousands of quasars that are not near an active galactic nuclei. So essentially, that mechanism to explain the redshift can be rejected because we see lots of quasars that are redshifted without it. And then there's also the idea of redshift periodicity, which was just a statistical effect that went away. So anyways, I already mentioned hydrogen, so on and so forth. So you could look at these spectra. Let's look at the Hubble's law just in a little bit of detail here. We're just about done with this little section. Here's Hubble's data in 1929. So this was the recession velocity versus the distance. And the distance, by and large, could be determined from Cepheid stars. Now, of course, you would have a limit in terms of that. And then this created a sort of cosmic ladder, though, where things that were really close, we could use the parallax. And things that are a little bit farther, we could use the Cepheid method. And things that are a little bit farther than that, we could compare them, though, and see if the results were consistent by using different methods in terms of how they overlap. And then some more data was collected, so on and so forth. And then what will it look like today? Well, it looks really, 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 really good in terms of describing the overall expansion of the universe. We're going to come back to this graph in particular, and what we can learn from Hubble's law. I mean, it's really a good, nice approximation for things that are relatively close, but it turns out the universe is more accurately governed, but in its expansion, by the Friedmann equations, which we'll spend a decent amount of time on here in a little bit. But anyways, this is a good understanding that, hey, Hubble's law and this understanding of the expansion of the universe works really, really well out to a good 7 billion light years, was about how far this goes away. And then we start to see some deviations from this the farther away we go. And so why is that the case? And what does that mean for our universe? But really, this diagram in here corresponds to a distance of 1.8 billion light years. I mean, this is a phenomenal picture of our universe. And each one of those dots is not just a star, but it's a galaxy. And in terms of the size and scale of our universe, it's really hard to fathom and comprehend. For most people, this is not going to impact their lives at all in terms of the size and scale of the universe, but at the same time, certainly it's much, much bigger than anyone could have ever imagined in the history of humanity. And we're going to, again, come back to this diagram also in discussing dark matter in terms of different hypotheses for what dark matter could be, how can you explain the various observations that we have, so on and so forth. But these are just some of the basics for how we can measure things about the universe. And then a crude little calculation of Hubble's law is something like this. Now, I never suggest actually using Hubble's law to calculate the age of the universe or anything like that. I would use the Friedmann equations. But anyways, here is a nice little example of that. So, Hubble's law it plots the speed of some object versus the distance. And if you go ahead and you find that there's some kind of correlation or trend between the two, so you could do something pretty interesting here. If you look at the units of this, V has units of meters per second, and then D has units of meters, so that means that this Hubble's constant, h naught, would have to have dimensions of inverse time. And really what this is it's a measure of how fast objects are moving away from each other. And so the idea then is that, well, if that's the case, then at some point the objects would have been touching. They would have been closer together in the past. And so you could do a little calculation like this and find that in order to figure out the amount of time since this is past, you basically take the inverse of the Hubble parameter. And you find that if you do this based upon some pretty close measurements of the Hubble constant, you find that it's about 2.3 times 10 to the negative 18 seconds. You can take the inverse and find that, approximately speaking, given the present rate of expansion, you find that the universe would have been together about 13.8 billion years ago. So you can get even a lot more precise using the Friedmann equations, but that's just an example of some of the basics of how we can measure some things about the universe, in particular, how we can measure how far away things are. So we're going to pause on that for now, and we'll come back to a few other interesting questions on these topics.